Okay, so hello everyone. Welcome to Stat 479 Lecture 11. Um, so today we're moving on to a very important topic in multivariate statistics. So we started to talk about that in Lecture 10, which is this notion of regularization. And in particular, we're going to talk about a very common and probably the most widely used form of regularization, which is ridge regression. It's also sometimes it's referred to in the mathematics community as Tikhonov regularization, which more or less just means adding like the regularization functions just an L2 penalty. In particular, we're going to focus on kind of the analysis, and that'll relate to bias and variance, which are terms we introduced earlier. And the real goal is to kind of show what the benefits of this L2 regularization actually is. So just to kind of recap what we talked about at the end of the previous lecture with regards to regularization. So the general regularization objective is as follows. So you essentially have like your data fit or negative log likelihood objective. So for the first two modules, which are which are linear models and then generalized linear models, we typically just solved we just minimize this negative log likelihood objective. But now what we're doing is we're going to minimize a combination of this negative log likelihood objective plus some regularization function. And just to kind of this sort of general framework's pretty general of like having a loss function or negative log likelihood objective plus a regularization, so that negative log likelihood sometimes referred to as a loss function. It's also referred to as a data fit term sometimes. And then that second term has a regularization parameter lambda. So this lambda is always it's bigger than zero, I should say. And R of B is a regularization function. And so today we're going to focus on the specific case of like where R of B is the squared L2 norm of B, or the sum of the BJ's squared. And so for those of you who haven't heard this notion before, and that I suspect that's a number of you, I think the question to kind of keep in the back of your mind is like, what are the benefits of regularization? In particular, we'll see that there are kind of greater benefits when you really move to the multivariate setting. Like that's something to kind of really think about. And I did highlight them and list them in the previous lecture, but I kind of just stated them in words. And so hopefully some of the analysis that we're going to do today is going to shed some light as to what the actual benefits of regularization are, particularly firstly in the squared L2 case, and then in a couple of lectures we'll move on to the L1 case. So let's go back to our statistical framework. So here, our data again is kind of what we've seen for the so we're going to work in a pretty standard setting today. So we have our typical data here, and I'm going to again kind of use this very convenient matrix vector representation. Okay, and so that's because, as we'll see later, we're going to use the linear model, and that matrix vector representation is going to be kind of the easiest way to represent this. And so here we're going to use the standard linear model. I'm going to talk about generalizing beyond the linear model to kind of like, generalize linear models right at the end. But the focus of today's lecture is really going to be on the analysis side, and we're going to see that that's a lot easier when you're focusing on the standard linear model. So in that case, you can write it out. I'll just to be explicit, just write it out in this way. Okay, and we're assuming things are independent. And we're also assuming that epsilon I, for convenience, is just normal with mean 0 and variance sigma squared. And they're also independent. It's also in matrix vector notation. That's just the same as what we've seen before. B here is in R to the P. And epsilon here is going to be a multivariate normal now with mean 0 and covariance sigma squared. And then standard, we have homoscedastic noise in this case, because that'll make things, as we'll see, that it'll kind of make the analysis that we do later a lot easier. And so this is kind of just the setting we had for linear models. But what's going to change, as we'll see, is we're going to use a different objective. We're not going to use least squares or maximum likelihood. We're going to use regularized, and least squares and maximum likelihood are the same in this case, but we're going to use a regularized version of that. Okay, and we'll also see and upfront, I'll say we're also going to place some additional assumptions on X later. We'll talk about what those are. Remember that the main focus of today's lecture is to do some analysis to kind of see what the benefits of regularization actually are, particularly when you're looking at kind of the squared L2 norm. Okay, so the third aspect of the framework is the estimator / algorithm. So that's this is where we're going to use regularization. So I'm going to use this So because it's because we're dealing with a Gaussian linear model, the negative log likelihood is just the same as the least squares objective, and because we're in the setting where we're looking at the L2 norm, we're going to add the squared L2 norm for the regularization. Okay, and so we're going to talk about how to solve that shortly, and then we want we're going to spend a lot of time in this lecture and the next lecture talking about the analysis. So the question is like, how close is beta hat R to, or B hat R to B? And importantly here, and how does lambda influence Okay, so today the main focus is really on the third and the fourth component of this framework. So if we look at the third component, which is the so then we have that the first thing to notice is that for lambda bigger than 0, pretty cool things happen, which is that that the beta hat R is unique and has very simple closed form. So how can we kind of see that? So what we can do is we can just differentiate and set to zero. And so why is this true? Because we know that so norm of beta squared is strictly convex. So therefore, obviously, if lambda is bigger than zero, then lambda norm beta squared is also strictly convex. And then we also know that y is convex. And so this means that beta hat r is unique. So remember that when we had the case where lambda is zero, if we wanted uniqueness, we had to kind of invert that matrix, which required rank of x to equal p when we had lambda equals zero. So in this particular case, if lambda is bigger than zero, we don't need that condition anymore. So because if rank of x is less than p, as we talked about before, you can't really invert that matrix, and which I guess we'll see again, but we talked about earlier. So we don't need any conditions on the rank here like we did before. So so to find b hat r in closed form, we just simply differentiate and set to zero. So if we let f of b be our objective function that we're looking to minimize, okay, then we want to just set the gradient equal to zero. And because things are quadratic, the gradients just end up being nice and linear. And so we've already seen what the gradient of that first term is. We know that from the least squares. And the second term, there's a 2 there, and the second term ends up being just because it's a quadratic. We can see that you just get the when you differentiate each term squared, you're just going to get that linear term, and so that whole thing is just zero. And so to simplify that, you can write that out as, if you want to isolate the b on one side and everything to do with y on the other side, you end up with, okay. So this is exactly like the normal equations, but we have this extra term here. So if lambda was zero, we would just have the standard normal equations like we had before. Okay, and this is, as I mentioned, why we don't need that condition on, we don't need that additional condition anymore on the rank, because this matrix, so we know that x transpose x lambda I is always invertible for lambda bigger than zero, right? We don't, this matrix is always going to be invertible because that's the identity. And to be clear, I guess I'll write this out. This is the identity with p dimensions. And so okay, and so this is pretty nice, and so know that this has all the nice properties. So b hat r is this is a linear function of y, right? So we know that so you can think of b hat r just being equal to a times y, where a is in r to the p by n, where a equals so this is like the least squares estimator in that sense, that essentially all that we're doing is just multiplying by some linear matrix, and that matrix here happens to be x transpose x plus lambda I inverse x transpose. And so this also means that it has a multivariate normal distribution. So since we know that y is multivariate normal with mean of xb and variance sigma squared I n by n, you can kind of show that or it follows that this is just multivariate normal with AXB and then sigma squared and then A transpose. Okay, and so this sort of this means that we have a lot of nice properties for this matrix, for this vector B hat R. We kind of know the whole distribution, and it has a pretty nice nice closed form, and that's going to be very useful for analysis that we'll see. So this is so one more thing to say about that. So to find B hat R, you can use gradient descent or any other approach for solving and so I mean in R this is in R or MATLAB or any other algorithm you might or any other package or program that you might use, you don't really have to do gradient descent. You can just say how do you invert a matrix, and there's packages that already invert matrices for you. So I'm not going to spend too much time on that. Okay, so in some sense, the algorithm part of this is not again too new or too different from what we've already seen. What's really kind of interesting and what we're going to focus on in today and then in this lecture and then the next lecture is the analysis. Which really asks the question, how close is B hat R to B? And so we're going to use this fact that that B we know that that B hat R is related to B through this expression where we have that this is what our A matrix is. Okay, so we're gonna make a very useful assumption here, and I'll talk a little bit about that soon. Okay, so what we're going to assume is that, so if you imagine here that the xi's here in R to the P, I've written it both in kind of matrix form, X transpose X over N, and the kind of the sum of n p-dimensional vectors times their transpose, so that should give you a P by P matrix. So this should be P by P matrix. You're adding up n of them. That should be the identity. So what that kind of means in principle, so this means that covariates are orthogonal, so independent, or covariates are orthogonal, I guess, let me... Or uncorrelated is another way to think about it. So we, in some sense, have features that are not really kind of greatly influencing each other. And appropriately normalized. So what that means is that we have that so the mean zero and variance appropriately scaled. So we ensure that so we have that norm of xi squared equals 1. So we have that the squared L2 norm is equal to so we have basically that the summation of xi all right. So another way to think about it is that if you add up all the xij's, it's 0, and if you that equals 1 for all I. Okay, so this is something you can actually often enforce on your data, that you're you can enforce these conditions, but what is difficult to enforce is that so normalization can be enforced or enforced, but orthogonal or uncorrelated features it's more difficult to force that. You can do that you can do that by kind of multiplying by an appropriate transformation matrix. We're not going to kind of get into too much detail on that. So I would say for many feature matrices so many feature matrices or covariant matrices X approximately follow this assumption. So for example, the one you used in your homework 1, for example, the way you generated that X, that won't follow this assumption exactly, but it will actually it'll get very close to following that assumption. I mean, there are results to show that if you kind of generate your features randomly like that it will follow that assumption. But as I mentioned, you can actually force this assumption to kind of be approximately true by essentially transforming your features a little bit. But again, and we'll see sort of why this is a very useful assumption in when we go through the analysis. So just to repeat after that kind of rather long-winded discussion, just wanted to remind everyone that we're assuming that X transpose X over N equals the identity, and that's the P by P identity. So why is this a useful thing to do? So let's see so remember that we have that B hat R is multivariate normal AXB, and then sigma squared A transpose, where this is what our A matrix is. Okay, so now if we have that X transpose X is equal to that, then we can say that A since we know that X transpose X equals to N times the identity, then you got a lot of really nice cancellations here. You get that this is just 1 over N plus lambda multiplied by X transpose is now our A matrix, right? And you also get that A times A transpose is okay, and so a lot of really nice cancellations here happen. As you can see, you're just going to get N plus lambda inverse then times N times N plus lambda inverse, and then all times the identity. And so you're just going to get that this is N over N plus lambda squared. And then this is times the P by P identity matrix. And you also clearly have that AX here is just equal to, and so that's just equal to N over N plus lambda times the identity. Okay, and so in that case, you kind of get a very, very nice simple expression for what our distribution of B hat R is, and all the x's very nicely just disappear, and you end up with N over N plus lambda times B, and then you end up with N over N plus lambda squared times sigma squared identity as the covariance matrix. So you get this very, very nice expression that's going to make kind of analysis a lot easier. So we actually have so we actually have the beta hat R's. The B hat R's are actually kind of independent, and so you can actually because since covariance is a constant multiplied by the identity. Okay. And so another thing you can just say is that we have that beta hat R, and then I'll use this J is just going to be normal N over N plus lambda times Bj, and then N sigma squared over N plus lambda squared. So this is a univariate type of distribution, and there beta hat RJs are independent. Okay, and this is one of the very nice consequences we get because we're assuming that X transpose X over N is the identity. If you don't assume that, you can still do a similar analysis. It just gets a lot more messy because you essentially have to transform to a set of features or coordinates where you do get this kind of nice this nice simplification that we have here. Okay, and I will talk about that later once we've done the analysis in this case, because the point is to see the analysis in this case, because that's hopefully going to shed some light. So just going back to analysis, so how close is and so we're again going to use, we're going to use one metric here, which is similar to what we've seen before, which is the expected value of beta hat r minus b, or b hat r minus b squared. And also note that this is exactly the same in this case as so under this assumption that since we have that x transpose x over n equals the identity, these two metrics are the same, so we're only going to focus on this one metric. Okay, and so once again, remember that this is equal to, we can kind of write this out in this convenient way as and so this is the variance term, the variance of b hat r in this p-dimensional case, and then plus. So this goes back to this this bias variance trade-off that we saw. So this is just so I did this calculation in about maybe the fourth or fifth lecture. So this is kind of the multi-dimensional bias and variance here. Okay, and so and we also know that we were in this very nice setting where we have the multivariate normal in kind of a nice simple form. Recall here it's just okay, and so let's look at the bias of b hat r here. So again, we can actually do this in a simpler way, because we can look at it component by component. Okay, so clearly because we're in this multivariate normal setting, we know that E of b hat r j is just n over n plus lambda times bj, or equivalently the expectation of b hat r is just n over n plus lambda times b. And so if we look at the expectation of b hat r minus b, so this is the bias. So that's just going to be n over n plus lambda b minus b all squared, which is just so lambda over n plus lambda squared times norm of b squared. So note B hat R is biased, and this is basically an artifact of all irregularized estimators. They're always biased because once you add that penalty term, that always biases your estimate in a certain way. So you can clearly see this is biased for lambda bigger than 0. So you can clearly see that the bias goes away to 0 because you go back to the least squares estimator when lambda is 0. But for lambda bigger than 0, this is biased. And so why introduce bias is the natural question. And hopefully, if you sort of think along those lines, hopefully there's some benefit in terms of the variance, and that's what we're going to get to here. So if we look at the variance of if we go look at kind of the variance of beta hat rj for each term is just equal to we've already worked that out. It's sorry. And so if you add that all up, because they're independent, therefore if you look at this is the variance of B hat R. So that's just going to be equal to, you're going to add that up n times. Times sigma squared. So you're just going to get P sigma squared over n plus lambda squared times n. Okay, so the upshot is that we have so we're going to have a bias term plus a variance term. Okay, so this is the squared bias. This is the variance. So one thing to note here is that essentially lambda trades off bias and variance. And this is a very common theme of these kind of regularization types of objectives, that for large lambda, large bias, but the advantage here you can see is that small variance. Okay, because you can see that in the above expression here we have an n plus lambda squared, so it appears on the denominator, and so you're going to get, as lambda gets bigger, that variance is going to get smaller. But then on the other hand, if you make lambda bigger, you have this this is clearly going to be a function where as lambda grows, like the bias is going to get bigger. So you can see that the least squares estimator, where lambda is 0, has no bias, and the variance is kind of large as it could be according to this expression. So for lambda equals 0, and so this is beta hat ls or beta hat ml because they're equivalent in this case. We have So in that case, we get P sigma squared over N. And you can see that that exactly agrees. So we did this calculation actually way back when we did the first module on linear models, and you get exactly the same result here. Okay, so you can see that we get kind of the same result. So we get, so the way to think about it is that the bias equals 0 because it's unbiased as we found out before, but the variance is P sigma squared over N. So let's look at to see some examples of when this might be beneficial. So let's take some concrete examples. So let's just first remember these formulas here. So we have that B hat R minus B squared equals so it's going to be okay, and so we have that also that the least squares estimator, which is just P sigma squared over N. Okay, and this is if you just plug in lambda equals 0, you get exactly that, and that's kind of what you expect, because if you plug in lambda equals 0, there's no regularization, you just have the least squares estimate. Okay, so let's think about some examples. So let's say that we have this extreme case where where norm of B squared is equal to 0, so B equals 0, and then we have lambda is equal to N. So we can see that in that case that so because the norm of B squared is 0, the bias goes away conveniently. That's usually not always going to happen, but it does in this case. But then if you plug in lambda equals N, then you can see that the mean squared error that you're going to get in this case is just P sigma squared times N over and then 2N squared. So you're just going to get P sigma squared over 4N, and then compare that to you're going to get the same mean squared error as P sigma squared over N. So clearly beta hat R is 4 times better. Since using because variance gets significantly reduced. Okay, so I mean that's kind of one example, but you kind of might say, well, you've kind of cheated a little bit by making that norm of B squared equals 0, which is making the bias conveniently disappear, and that's certainly a fair point. So let's look at another example where we're just now going to say that the norm of B squared is 1, so there is going to be some bias in this. We're going to set lambda equals N, and we're going to set P to be 100, and N to be 200 in this case, and then we're going to also set sigma squared here is going to be equal to 4. Okay, so here this is a setting where we're setting kind of everything up, and we're going to compare these two estimates. So you can see that now we're going to get a bias because we have So if we look at the bias term and plug that in, you're just going to get n over 2n squared times 1. So this is going to be, so this is the bias term. And then for the variance term, you're going to get 100 times 4, and then times again n over 2n squared. Okay. Okay, so in this case, you're going to get just a 1 over 4 times n, and then times plus 100 times 4 over 4 times n. So this is, and then if you plug in n equals 100 in there, you're going to get you're going to get 1 over 400 plus 100 times 4 over 800. So this is 800, I believe, now. Okay, I don't know if I've done this all correct, but I hope so. And so you should get 1/2 plus, let me see if I've done this correctly. So if the norm of, no, so that isn't correct. So you should get, this shouldn't be 1 over 800, sorry. So you should get a quarter, and so that should be 1/2 plus a quarter, which should be 3/4, hopefully. So you can check that. And then now let's compare that to the least squares estimate. And so that's going to be P times sigma squared over n, which is just 100 times 4 over 200, which is going to be 2. So once again, you can see that in this case, even though we have bias, beta hat R reduces MSE, reduces the MSE, because variance reduction is greater. Okay, and so on the other hand, if you took exactly that that same example, but now you changed, norm of b squared equal to 100, and then you have, n equals 100, p equals n equals 200, p equals 100, and sigma squared equals to 4. You can see that in that case, the expectation of beta hat r minus b squared is going to be pretty bad here, because and so here, L lambda equals n, then you're just going to get a quarter times norm of b squared, which is plus the term of 1/2 that we got before, so you're going to get 25.5, and then obviously the least squares doesn't change because all you've changed is the because all you've actually changed is the bias of the least squares, and going to change, and so this is going to again be 2, So therefore, beta hat R much worse than B, since you induce a huge bias. Okay. So just to comment on these results, so you can see that this B hat R allows the flexibility to reduce the mean squared error by trading off the bias and the variance through this parameter lambda. So you can, another way to think about it is that there's no real downside to using regularization, because you could argue that, well, if you don't really want any bias, just set lambda equals 0. So if you don't want bias, just set lambda to 0. And you get back to your just, and then, you have the beta hat R just equals to the beta hat LS, okay? And so then you're not really losing or gaining anything. But here we actually have we essentially have a broader set of methods, because lambda can vary. It can be anything bigger than 0, so lambda being from 0 to infinity. So sorry, I don't know if I mentioned explicitly that lambda's has to be greater than or equal to 0. But there's no, so you can in some sense have a broader class of algorithms, essentially a broader class of estimators which depends on lambda. Okay, and so clearly as beta 2 gets larger, you want lambda to be smaller. To reduce bias. And another way to think about that is if you keep same lambda as we did in that third example, so that's I guess what we have going on here is we have essentially we have the bias which is induced by the L2 norm of B, and then we also have lambda which can allow you to tune for that. So if you want to reduce the bias, you can just make lambda smaller. So another way to think about it is that so another way to interpret regularization is we can incorporate prior knowledge. So if the norm of B2 is small, set lambda larger to incorporate this knowledge. Okay, and so just to be clear, so for the purposes of the homework, so that's homework 3, I'm going to explicitly tell you how you're going to set lambda. In practice, and what you're going to be doing in the project, lambda is actually typically set by algorithms like cross-validation. I'm going to go through that not in this part because this part really focuses more on the theory and methodology. But in the last sort of 4 or 5 lectures, when I actually talk about what you do with real data, because like what you do with real data is you don't know what this L2 norm is on B. So you need a way to kind of set lambda for something like that, and there are ways to do that in practice, and I'll talk about those. So cross validation is one you may have heard of, some of you, but that, and so I'm going to talk about how we do that in the last sort of 4 or 5 lectures. Okay, so we've got kind of a couple of different a couple of different ways to see how there's potential benefits to doing regularization in the L2 case. And so just to kind of so there are a lot of natural generalizations of this. So if X transpose X on X is not the identity, so if that's not true, a similar conclusion holds. A similar conclusion holds, like the way you can kind of see that is that you just make X transpose X over N is equal to, so this is the eigen decomposition. Okay. So V is in R to the P by P diagonal, and we also have that V transpose equals V transpose V equals the identity. So this is okay. So this is the eigen decomposition, and so when you do that, you kind of diagonalize everything, because you by transforming it, you can get this kind of nice diagonalization. I'm not gonna kind of go through that explicitly here because it's essentially just linear algebra to do that. But that's like, so that assumption, I introduced that because it made the analysis a lot easier. But essentially, you can imagine that something like similar to that will hold. So if we had time, I might go back to this case, but the intuition stays pretty similar. Okay, and then to any log likelihood / loss function. So so if we think about like GLMs, the likelihood objective part changes, and just add. We're going to add the squared L2 penalty. We're just going to add the squared L2 penalty in terms of the to this objective, and you can do that as well. And then another generalization is that if you believe B is not close, is if you believe that the L2 norm of B is not small, but the L2 norm of B minus B0 is small or close to a different point B0, you simply let R of B. Okay, so we talked about the L2 norm of B being small basically says that you believe that it's kind of close to the origin, but you may believe that you may have a priori belief that, hey, it might be close. We have some idea that these covariates have a high weight and these covariates have a low weight, and you might be able to include that through a different point B0. You can certainly use the a different regularization, and you'll get essentially similar conclusions. Okay, so that's kind of it for today. So we'll move on to we'll round up this discussion on the squared L2 on kind of the ridge regression or Tikhonov regularization in the next lecture, and then move on to the lasso or L1 regularization. Okay, thanks very much.